Okay, guys, here's the last part of the acid-base definitions that we're going to talk about. And this is some, other information about acid strengths. Okay, so we're going to talk about the difference between strong and weak acids. Strong acids and bases. Strong acids and bases completely dissociate. So when we talk about something like HCl, I know that gives me H plus Cl minus, right? And that's a complete dissociation. I do not have any HCl left. So whatever concentration this was, 0.1 molar, then that's the concentration of H plus and the Cl minus. The same would be true if we were talking about, I'm actually not going to use Mg, sorry, NaOH. That gives me an Na plus an OH minus. If this were 0.1 molar, if we added enough to make a 0.1 molar NaOH, then the concentration of the Na plus would be 0.1 molar, and the concentration of the OH minus would be 0.1 molar. Now understand that this is a little bit different when we're talking about a polyatomic ion. So if I have an H2SO4, right? While that first proton donation is strong, and it's all going to happen, so we're going to get HSO4 minus plus H plus, and so whatever concentration I had here is going to be my 0.1 molar here and my 0.1 molar here. I know that this HSO4 minus, this species right here, can further break down to become SO4 minus. And the degree to which that happens, we don't know how to look at yet, okay? The other thing that I have to point out to you is that when that happens, and we go HSO4 minus to give me H plus SO4 minus, I don't know how much of that happens. But I also know that I now have more H plus than what I had simply from the first dissociation. And so how much of that I have, I don't know. So the stoichiometry there gives us some indication that it's going to be more than 0.1, but it's not going to go all the way to 0.2, okay? Which is what it would be if this second dissociation was complete, all right? On the other hand, if we were to look at an MgOH2, that gives me Mg2 plus 2 OH minus, and that is complete, okay? That is complete. That happens in 2 steps, so both of them are complete. It is completely dissociated. So if I had a 0.1 molar solution here, I get a 0.1 molar Mg2 plus, that should be a concentration. And I'd have a 0.2 molar OH minus. Okay, so keep that in mind when we're calculating pHs and pOHs and things like that. If it's a strong acid, you should know what those concentrations are. If it's a strong base, you should know what those concentrations are. And so that's important, all right? I'm going to talk about just a little bit about what else is on this slide. You'll see that I have an HA plus an H2O. Now, I've talked about that A before. That represents an anion. Okay, I don't care what that anion is. So that A is just the anion. So we use that to talk about generic acids. All right. We can do the same kind of thing when we talk about hydroxides. So hydroxides are almost always metal hydroxides. And so it's either going to be an MOH or an MOH2. Okay, so we're going to have to look at which one of those it is when we talk about those metal hydroxides. But when we talk about a generic hydroxide, you'll see something that's an MOH or an MOH2, and that will tell you what the charge is on those things. So if it's a 2 plus, then it's one of my alkaline earth metals. If it's a 1 plus, it's an alkaline metal. Okay, so that gives you some indication there. All right, hopefully there are no questions about that. So we know that they're completely dissociated. We know what those concentrations are, all right? Now, if it's a strong acid, it's not a weak acid. It completely dissociates to give that all of its H plus to H over to water to make that H3O plus. Okay. If it's a weak acid, that means it doesn't completely dissociate. I mean, that is the definition that we have. And the amount that it comes apart is based on the K for that reaction. So now that we know something about the Ks, we can look at how good is that acid based on that. And that's what we're going to do next time, all right? We'll be able to find the H plus concentration. We'll be able to find what the A minus concentrations are based on that, okay? Now, another thing I'm going to tell you, if it is not a strong acid, it is weak. So if it is listed in the strong acid table, if it is listed in the strong base table, it's strong. If I ask you about anything else, whether it be in a list of weak bases, weak acids, whatever, if it's not in that list, it's weak. Okay, and you can assume that the behavior is based on that K. All right, so that's an important thing for you to understand. Calculations and questions. Let's do some calculations and questions. We'll do one set of this. I think that's the only one we're going to do. Yep. So, what is the pH of a 0.0235 molar HCl? So HCl, strong acid. So if it's a 0.0235 molar HCl, it's a 0.0235 molar H plus. I take the negative log of that to determine the pH. And what do I get when I do that? The negative log of 0.0235, and I get 1.63. Okay. And it's 628. Now, let me talk about that in just a second. Looking at this number, the 0.0235 has 3 significant digits. The zeros in the front are not significant. The 2, 3, and 5 are. So I have 3 significant digits that I need to worry about for that. When I take the negative log, that affects how many numbers that I have. The thing out in front of that log, that number that I get, so the part that's not a decimal is not important. I don't count that. What I count is how many decimal places I have. So I had 3 significant digits here in the 0.0235, 3 there. That means I need 3 decimal places on my logarithm. Okay, so that's how that works. The number of sig figs you have here becomes the number of decimal places here. You'll see that there are sometimes a lot of them. It feels very weird to people to see that. That is what is expected when you report those. Okay, so what's the pOH of that solution? Well, my pOH is equal to the pH, it's equal to 14 minus the pH, which is equal to 14 minus the 1.629, and I can take 14 minus the answer and get 12.371. And again, 3 sig figs there, because we assume that the 14 is 14 as many sig figs as we need. So we're going to define how many decimal places we have based on the 1.629. Okay, so that's my pOH. If I want to know what my OH minus is, OH minus is equal to 10 to the negative pOH, so to the negative 12.371. And that's equal to second times negative second answer, 4.256 times 10 to the minus 13th is the concentration that I get there. The next question that they ask you is, what is the H plus? Well, I know what the H plus is because that's the first thing that I answered, that I needed that to get to my pH. Now, is this the only way that I can do this? No, absolutely not. Okay, there are other ways that we can manage this. But since the only thing I knew in the beginning was the H plus concentration, I had to go from H plus to something. Now I can go from H plus to OH minus. The other way I can calculate OH minus is to say 1 times 10 to the minus 14th divided by the 0.0235, and that should give me 4.256 times 10 to the minus 13th. It doesn't matter which way I get there. Both of them should give me the same answer. And of course, once you have an OH minus, you can take the negative log of that to get the POH. So if you are more comfortable doing it that way, that is perfectly fine. I don't care how you get there. I just care that you get there. All right. My second question says, a solution is created by measuring 3.60 times 10 to the minus 3 moles of NaOH and 5.95 times 10 to the minus 4th, 5.95 times 10 to the minus 4th moles of HCl into a container, and then water is added until the final volume is 1 liter. 1.00 liter when they're added together and diluted. What are the H plus and the OH minus? What's the pH? What's the POH? So same 4 things that I'm looking for. Now remember, we have NaOH plus HCl going to give me NaCl plus H2O. I have in this 3.60 times 10 to the minus 3 moles of NaOH and 5.95 times 10 to the minus 4th moles of HCl. Obviously, one of those is smaller than the other, and that determines that I have a limiting reagent, which will determine how much H2O I can make. Okay, so since the smaller number is the 5.95 times 10 to the minus 4th, I know that that determines that amount of HCl will react with the NaOH, right? So I can take the concentration of the NaOH, the 3.60 times 10 to the minus 3, and subtract out the 5.95 times 10 to the minus 4th, because I know that for every HCl that reacts, I have to use up an NaOH. So that will give me the concentration of NaOH that is left. So I can take my 3.60 times 10 to the negative 3rd, and I subtract the 5.95 to the negative 4th. And that gives me 3.005 times 10 to the minus 3rd. Now, is that really the right number of sig figs? No, it really isn't. It should be 3.01, but I'm leaving it for illustrative purposes here. Okay, so that's how much OH minus I have left. Because remember, this was NaOH, this was HCl, and that is in moles. We have not converted to molarity, so that's the number of moles that I have left. I need to take and divide that number of moles by the 1 liter, which then turns it into molarity, which of course I cheated. I give you a 1 liter container, so there you go. So your molarity of OH minus is 3.005 times 10 to the minus 3rd. If that's how much OH I have left, I take the negative log of the 3.005 times 10 to the minus 3rd, and that will give me my POH. I take the negative log of that lovely answer that I calculated, and that gives me 2.52. And that's my POH. Now, pH equals 14 minus the 2.52. 11.48. Okay, and that's my pH. I also need to know what is the concentration of H plus. So if I want to calculate a concentration of H plus, that's equal to 10 to the negative 11.48. So I take second 10x negative second answer, and that gives me 3.33 times 10 to the minus 12. So those are all 4 of the answers that I was asked to find. Okay. The big thing here becomes in recognizing that these 2 things are going to react. One of them is consumed. The HCl is completely consumed. We have OH left, and that's what determines the OH minus concentration, which then determines the POH, which then determines the pH, which then determines the H plus. Okay, so it's a big, huge circle of things that we're going to calculate. Do you have any questions about that? Questions, comments, problems? I hope not. But if you do, please let me know. Again, there's lots of practice for working with the fun box. Make sure that you have done your practice so that you don't need to take a bunch of time on the test to do this, all right? If you have any questions, let me know. Otherwise, we are done with our acid-base definitions, and I will see you soon.